Hey everyone, thank you so much for attending my talk on vector search for data scientists, including a case study with Twitter analytics to hopefully further clarify this idea of what vector search is and what it can add to the typical workflow of data scientists. And before getting into the presentation, I also just wanted to thank the ODSC people for all their help with the webinar software and allowing me to speak. Super excited about this opportunity. So let's begin by kind of getting into how I'm defining data science and how I'm looking at vector search. So some of the common questions in data science that we want to answer are things like, how is my data distributed? Are there outliers in my data? And are my variables correlated with each other? And so when we have things like Twitter analytics, we have a collection of our tweets, and we have data like the number of impressions or URL clicks that we're getting on these tweets. So we want to look at how those kinds of metrics are distributed, say it's normally distributed or power law distributed. And then this third thing, we want to see how it varies with respect to other variables. So for example, what time of day we're sending the tweet, or whether the tweet has a URL in it. We want to understand how that impacts the distribution of metrics like impressions or URL clicks. So this is kind of the primer on the questions that I'm looking at when I refer to data science. And to now bring vector search into the picture, vector search is this idea of representing objects as vector representations extracted from deep learning models. And the idea is, can we capture the semantics of the raw content of our data in these vector representations such that we can learn something about our data from the semantic clusters extracted from these vector representations? So to bridge these together, I'm going to be using the case study of analyzing my own Twitter analytics. I've been working for a while on making content on social media about different topics in deep learning, and I've been very interested in this question of, say, which topics to focus on, particularly how to deliver these messages. And so I think it's a fun example to look at this idea of vector representations of the tweets themselves and see if that enables some novel analysis of the metrics like impression count, engagement rate, and these kinds of things. So if you want to do this for yourself on your own Twitter data, you can easily go to Twitter Analytics, and they have a dashboard to extract, I think, up to 4 to 5 months of your recent Twitter data in a CSV file. And I'll be showing you how to upload that into the Weaviate Vector Search Engine and do all this kind of exciting analysis. So as mentioned before, when you go to the Twitter Analytics data, you'll get a CSV like this, where you have the raw text of the tweets themselves, what time the tweet was sent, as well as the metrics that we're interested in, like impressions, engagement rate, retweets, replies, likes, user profile clicks, and URL clicks. So to kind of preview the theme of this talk, usually what we would do is we would try to do some kind of manual feature engineering to create symbols from the content of our tweet. So does the tweet contain an emoji? What's the word count of the tweet? Or does it contain particular phrases like Weaviate or deep learning? In this talk, we're going to be trying to just take this text data and pass it into an inference of a natural language processing model that's going to produce a vector representation of the raw text itself. We're going to be clustering these text vectors to try to get a sense of the content of the text and how we can segment our analytics based on this content. So to take a step back, there are 5 main takeaways that organize this talk on vector search for data science. We have the first part on segmentation and data science, understanding how we segment analytics based on other attributes in our data. The second key theme are vector representations of data, understanding how we can form vectors that represent our data and capture the semantics in our data. The third key part of this is vector segmentation, using these vector representations to segment the analytics in our data. And then the fourth section that I'm really excited about is to demonstrate Weaviate for Twitter analytics, show some cool things that we can do with the Weaviate Vector Search Engine to illustrate bringing all these ideas together in a real application that is very exciting to me, so I hope it interests you as well. And then finally, we'll conclude with some research questions and discussion about trying to improve these kinds of systems. The first key takeaway is to understand segmentation in data science. So when we're looking at data sets, we often have some metric that we're interested in, like the impressions on tweets. It could be clicks on an ad, say views on a YouTube video, downloads in a GitHub repository, all these kinds of things. We have metrics, and we want to look at some kind of distribution of these metrics. So first we look at the distribution, and then we want to see how that distribution varies with respect to other attributes in our data set. So this is the idea behind segmentation in data science. We want to ask questions like, how does this distribution vary based on what time the tweet was sent, or is there a URL link in the tweet? And these are examples of symbolic segmentation. We have these symbols, features in our data set that we can use to separate out distributions and and have this kind of correlation analysis between variables and other values that we're interested in. And this will transition us into this idea of, instead of symbolic attributes, segmenting analytics based on vector representations. So the first question, to give an illustrative example, is this question of what time was the tweet sent? So we start off with our original distribution of the impressions on all the tweets, and then we look at how this varies on tweets that are sent before 12 p.m. or tweets sent after 12 p.m. And this is an illustration of how we can use these symbolic attributes to get a better sense of our data and see how it varies with particular things. Similarly, we might ask, does having a URL in the tweet, does that have a major impact on the number of impressions that a tweet receives? And so we split our data based on the value of having a URL or not having a URL. The big question in this talk is, can we split the impressions based on the semantics of the content itself? Can we take the raw text of the tweet, or say the raw content of a YouTube video, or maybe the visual style of houses and all sorts of things as we get into more examples, but can we split the impressions or split any kind of metric based on the semantics of the content and extract the semantics of the content from vector representations? So for example, we might want to split these tweets based on tweets that are about the Weaviate podcast, Weaviate tutorial, or AI weekly update. Similarly, we might want to split the tweets that are based on different topics in deep learning, like say natural language processing, computer vision, or robotics, and see how each of these different semantic categories of tweets are performing with respect to our impressions metric. And we can do this with the search interface, where we just use the query point of the topic natural language processing, encode that into a vector representation, and then use the nearest neighbor distance between the encoding of natural language processing and all the tweets that I've tweeted out, and use those distances to get the cluster of tweets related semantically to natural language processing. So we can segment analytics based on the semantics of all kinds of data. This example is going to be focusing on text and tweets, but we could also do this with images and visual styles. Increasingly, this is becoming successful for encoding code itself, audio, video, graph structure, biological sequences. You really can encode all sorts of things in vector representations, which is a big part of what I think makes this so exciting. To summarize the first key takeaway in this talk, we can visualize the distribution of our data to get a sense of it. So for example, we see that impressions are somewhat normally distributed. And we ask questions like, well, is this distribution also the case for tweets that were sent at, say, 3 in the morning? And now the question that we're trying to ask is, what about tweets related to deep learning for robotics? And we're not going to be doing this with an exact keyword match of robotics or the phrase deep learning for robotics. Rather, we're going to use deep learning models to make predictions about vector representations of the phrase deep learning for robotics and map it in a vector space to other tweets in the data set. So let's take a step back and jump into the second key takeaway about understanding vector representations of data, diving deeper into exactly what these vectors are, how we get them, how we compute distances between them. So we'll begin by describing symbols compared to vectors. So in symbols, we have things like, say, categories. So for example, if we have a vehicle category and we have vehicles like airplane, truck, car, motorcycle, we would use this one hot vector to denote that this is a truck. So we use these kinds of categories to illustrate things. Similarly, we have numeric values like, say, the age or the weight of a person, or we have Boolean values that take on these 0, 1 values. Compared to vectors, which are a different way of representing things, where we have some n-dimensional object that has some value in each index of the vector, and we use this to form our representation of whatever real-world thing it is that we're trying to describe. So the way that we get these vector representations of data is we can take in any kind of data. It could be text, it could be images, audio, video. In this particular example, we see these high-dimensional, high-resolution images of golden retriever puppies that we map into vector representations of data. So we take this, say, height by width by red, green, blue channel image tensor, and we compress it into a vector. So we have vector representations of all the images in our data set. Once we have these vectors that represent the images, we can ask questions like, are these puppies semantically similar, by using vector distance calculations. So a very common vector distance calculation is L2 distance. This is where we loop through each index of the vector and then sum up the square difference between the two indexes of the vector. So for example, say the first puppy image is mapped to the vector 4, 8, 10, and the second puppy is mapped to 2, 9, 11. And then let's pretend that there's some third image of an airplane in the sky, and that has the vector representation 1, 20, 20. So we're going to loop through each of these vectors to compute the L2 distances between them. And we see that we have 4 minus 2 squared is 4, 8 minus 9 squared, 1, 10 minus 11 squared is 1, sum that up to get 6. And we do the same thing between the puppy vector and the airplane vector and find that that L2 distance is 253. So because 253 is much larger than 6, we say that the first puppy is much more semantically similar to the second puppy than the airplane. So what we're going to be doing with our Twitter segmentation is we take concepts like natural language processing, encode them into vectors, and then compute the distance with the vector representations of all the tweets in my Twitter data set, and then determine which of the tweets are semantically similar to the concept of natural language processing. And so we have a very flexible interface to segment our data on whatever category we can come up with, because it is such a flexible interface to just encode anything into these vector spaces. And the idea is that we capture the semantics in these vector representations. So for example, as we have 300-dimensional vectors that have some value in each index, if we look at the low-dimensional projections, we see clusters of objects that are semantically similar, like this chicken, and then an actual image of a chicken, wolf, dog, cat, kitten. They're all in this kind of cluster compared to, say, the brand cluster with Google, Apple, and then, say, apple, banana, the actual fruits. And so it's worth describing quickly here why this talk is about vector search for data science rather than, say, just vector clustering for data science. We could take this kind of representation and do a k-means cluster and say, here's cluster 1, here's cluster 2. But what's more interesting about vector search is how we can have this titling to our cluster. We insert a query like animals, and the animals query takes us to these points in our data set. So it's not just a cluster, but it's also titled with the search of its distance to this query point. We can also have a query that says brand, and it brings us to the Google and Apple thing, or similarly fruit takes us to apple and banana. So we have this interface to have this semantic search of clusters in our data that are near some kind of concept that we're interested in splitting our data based on distance to. So let's talk a little further about how vectors represent real-world objects. You may be interested in how, say, a 384-dimensional vector that has a position in each of these index, how does that represent each of the things? So coming back to this semantic cluster example, to say the first index on the vector represent how much of a brand this particular point is, because you see this is like a Google logo and an Apple logo. Does this first index say how much of a brand this is? And this is a very interesting kind of discussion. There's a whole research field around this known as disentangled representation learning, and we really can't isolate the vector representation and just quickly turn it back into a set of symbolic attributes. Really, we have this entanglement and these interaction effects between all sorts of relationships in our data captured in this entire vector structure. So similarly, we might want to ask how well we can compress these vectors. And one of the most interesting experiences I've had at Weaviate is exploring this idea of binary passage retrieval, where say we compress vectors that have values like 0.34, 2.35, 8.34 into 1 or 0 values based on if they're greater than less than some threshold. And we found that this actually does still perform pretty well with retrieval, which I think is very interesting. Another very interesting idea is if we can compress, say, 384-dimensional vectors into, say, 32 dimensions with things like product quantization or locality-sensitive hashing. And it's a very interesting thing around managing these vectors and trying to optimize them for retrieval speed and storage optimization, which is one of the big things that we're looking at with the Weaviate Vector Search database. So now let's take a step back. Now that we've seen kind of what we do with these vectors, once we have vectors, we've seen what they are, we convert our data into vectors, we compute distances between vectors to say that they're semantically similar. We also can project them into low-dimensional spaces to visualize relationships or use query points to form semantic clusters. Now let's get into how we got the vectors to begin with. So this is one of the most influential papers in vector search, and particularly vector search applied to text, sentence embeddings using Siamese BERT networks. The idea behind this paper is to take a neural network architecture known as BERT. It's the whole abstraction that you need to know is that BERT is a very popular transformer neural network architecture, and it takes as input something like text, like a paragraph or just a single sentence, and then it produces a prediction. So we're going to be indexing that prediction to produce a vector representation that is one of the intermediate layers of a neural network like BERT. So BERT will map this sentence into several layers, and in these layers we can index and get a vector representation from BERT. So the idea is to have a Siamese architecture where we copy the same weights of the same BERT network and try to align these latent representations between similar positive scored A and B pairs. So we take sentence A that we determine to be semantically similar to sentence B, we pass each thing through the BERT network, and then we have these vectors that we optimize to have say a high cosine similarity between the positive pairs. And then we would put gradient descent back through each of these neural networks, optimizing them to produce representations that are similar for things that we've determined to be semantically similar. So where do we get these semantically similar points? Commonly, we're using things like heuristics, where we take internet scale data sets like Wikipedia or books, or these examples like MS Marco is a data set that contains query passage retrievals from the Bing search engine, and we use this to form these heuristics about positive pairs. So as an example sampled from Wikipedia, say we take this paragraph about the Miami Heat basketball team. So we have this text sequence that describes the Miami Heat basketball team, and we use heuristics like the neighboring paragraph to say this is a positive paragraph, and we should align these two representations in the vector space. So the vector representation of the Miami Heat are an American professional basketball team based in Miami, ... and then the vector representation of led by Wade and following a trade for former NBA most valuable player Shaquille O'Neal, ... The vector representations of those two paragraphs are going to be optimized to be similar to each other. A lot of frameworks also use negative points to normalize these representations and avoid the trivial solution where it just collapses to, say, a constant vector representation that would solve the optimization task of making every vector similar to each other. So we might sample something like, say, this paragraph from Wikipedia that describes deep learning to have some kind of normalization to the optimization of these vectors. Another interesting strategy is to not even bother with trying to come up with real examples of positive negative pairs in the world, but to just use this masking interface to form the positive pairs. So in this case, sentence A would be, I like tea with milk, and then the sentence B would be, I like tea, mask, milk. So this interface is very appealing because we can generalize it easily from text to speech to images to graph structure. Really anything can be amenable to this idea of just applying a noise mask to form the positive pair of the data point. So these are a couple of ways of thinking about how exactly we're going to get sentence A and sentence B, and there's even further research if you really want to get into the details of how we optimize neural networks to produce semantic vector representations of data. But you might be wondering, this might look intimidating. Do I need to train my own contrastive learning model? And one of the most interesting trends in deep learning lately has been increasingly no. There are many pre-trained models that work very well for a broad range of data. This is often known as zero-shot generalization. This idea that we can have a model that's trained on some data set like Wikipedia, or just like the colossal common crawl corpus, where we just do an internet scrape of text data and we can train a model such that it generalizes to all sorts of data distributions. So if you're interested in this, I highly recommend checking out the sentence transformers. These are great zero-shot models that will probably have a pretty good vector representation for most data domains, unless there's really particular language in the data domain. So to summarize the second key takeaway, data such as images, text, code, audio, video, these can be represented as vectors with deep learning. The deep learning models are trained to maximize the semantic similarity with these vectors, and they're usually optimized with absolutely massive collections of data. And this kind of helps it with that zero-shot generalization and generalizing to new data distributions right off the shelf from pre-trained checkpoints. So we often don't really need to train the models ourselves for particular data domains to reach reasonable performance, although we'll talk about this further later under the section of research questions. The third key idea is going to be to bring together these ideas of segmentation and data science, where we're splitting the analytics as well as these vector representations. So we saw how we can, so the motivation behind this talk is how can we segment analytics based on the semantics contained in the raw thing that we're trying to measure, like the text of the tweets, or say images of houses, code from GitHub repositories, audio from music files or sound effects, or videos from YouTube, and so on. So coming back to the Twitter example, how can we split the tweets based on whether they're about the Weaviate podcast, the Weaviate tutorial, AI Weekly Update, whether they're about natural language processing, computer vision, robotics, or say even niche research categories like self-supervised learning, data augmentation, active learning. How can we segment the tweets that are referring to this kind of topic without needing to manually label the tweets, and do this right off the shelf by using this vector search interface? So to kind of tie this together and explain this idea of vector segmentation, let's look at a couple more examples in addition to the Twitter idea to hopefully further cement this idea and clarify how we can do this vector segmentation for analytics. So let's start with the fun task of house hunting, and imagine that the metric that we care the most about is the price of the house. So mapping impressions of tweets to the price of the house. So usually with these real estate platforms, we have symbolic attributes like the number of bedrooms in the house, the number of bathrooms, square feet, the city that it's in, and we can use that kind of thing to segment out the price. Say we say, oh, the houses in Boston are clearly more expensive than houses in some other city, or houses that have greater than 3,000 square feet. Symbolic features like that to split out the segments of our data. But with vectors, we can do things like, say, take a picture of the front of the house and then segment the houses based on the visual aesthetic of the house. Coming into this idea of graph embeddings and things like graph neural networks, deep walk, we could also encode the neighborhood structure of the houses and segment the prices based on this graph structure of the neighborhoods. And then generally, if say we want to have features like, does the house have a pool in it, or things like that? Does it have a backyard? These kinds of things. The text interface of describing the house gives us a much more flexible way to define these features and then split houses that have these kinds of features. Another common example is to look at e-commerce products where we'd have symbols like shoes, t-shirt, pants, or colors of clothing. And then with the vectors, we can really encode the semantics of the visual styles of the e-commerce products. So movies, we have symbols like genres of children, action, sci-fi, and then the vectors can say you take the entire synopsis of the movie, you can take reviews of the movie, and you can use this to form embeddings of the movies that better capture the real content in the movies, rather than just looking at these symbolic attributes. And then we can use that to segment analytics like the box office numbers, how many people, or say the ratings of the movies, and things like the IMDb or Rotten Tomato kind of platforms. We can use these kind of vector embeddings of the content itself to segment those kinds of metrics. And then a really interesting idea is scientific papers, again, symbols, biology, machine learning, but with vectors, we can really encode the nuance of the ideas by putting the raw text in the scientific paper into these vector embedding spaces. And then finally, music, again, same idea, and that's the big idea. So let me end this section with a quote that I think really summarizes this idea well. That's the magic of deep learning, turning meaning into vectors, then into geometric spaces, and then incrementally learning complex geometric transformations that map one space to another. All you need are spaces of sufficiently high dimensionality in order to capture the full scope of the relationships found in the original data. And this is a quote from Francois Chalet in the second edition of Deep Learning with Python. So I really like this quote because it for one, it captures the four words that we're really here for, this idea of turning meaning into vectors, and describing that as being the magic of deep learning. The quote continues to kind of describe further how the magic of deep learning operates, having these sequential layers of nonlinear processing and mappings from one tensor space to another. But really, aside from the complexity of deep learning models and the sequential structure of them, the key idea is turning meaning into vectors. So to summarize the third takeaway on vector segmentation, vector representations, which are also commonly known as embeddings, enable this interface to split analytics based on the semantics of the content, and this doesn't require manual labeling, manual category tagging in order to do this. And this content could be text, images, code, audio, videos, really all sorts of things you can imagine can be turned into vector representations. So I'm super excited to be showing the fourth part of this talk, an illustration of applying Weaviate Vector Search for Twitter analytics. So to recap the original, the premise of the talk, so with Twitter Analytics, when you go to the Twitter Analytics dashboard, they give you this set of metrics. They give you the raw text in your tweets. They give you what time you had sent the tweet, the impressions, engagement rate, retweets, so on, the metrics that we're interested in looking at to understand how well the tweet is performed. So the first thing that we're going to do is define a Weaviate schema to be uploading our Twitter data into Weaviate. So the Weaviate schema interface in Python, it's a very flexible way to define these things, define data schema and upload your data into them. You have this dictionary where you can define more than one class. In this first example, we're just going to look at one class, which the name of it is tweet, and has different properties like the text that's in the tweet, who was the author of the tweet, and say the number of impressions, the URL clicks, and so on. So an interesting thing about looking at the schema is seeing that in the text-to-vec transformers, we tell Weaviate to vectorize this particular property of the tweet class, whereas with author, we'll tell it to skip that one and not use the author text to form a vector representation of the overall data object. So another thing that I thought was really interesting, and I thought would appeal to a conference like Open Data Science Conference, is the cloud data upload and how easy it is to go from Jupyter notebooks that are interfaced on the cloud through things like Google Colab and then into the Weaviate cloud service. So doing this with this Python data schema and looping through my tweets from CSV to pandas and then into this Weaviate schema, all of this can be done with this Jupyter Notebook interface, and it's just a couple of clicks going from the web-hosted Jupyter Notebook environment to the web-hosted Weaviate cloud service, where you can do things like query the data with the GraphQL console, or also query the data in Python as well, which I'll show you later in the presentation. So now that we've kind of explained the basics of defining the Weaviate schema and uploading the data, let's see a live demo of looking at my tweets in Weaviate. So shown on the screen is the Weaviate console, and this provides a GraphQL interface to query data, and personally I love this. I think it's so much fun to play around with this. So before we get started, I think a great way is to have a look at the schema. So as described, right now we have one class, which is a tweet, and it has properties like the text in the tweet, which is what we're going to be vectorizing with our sentence transformers. And then it has other things like who the author of the tweet was. It has say the time of the tweet, and then the impressions, which is what we're interested in. So what we're going to do is first we're going to do a semantic search where we're going to find tweets that are similar to the concept of natural language processing. So the way we do this is we have a get query with our GraphQL interface. We're going to be getting the tweet class, and then we're going to tell it what properties we want it to return. So let's see the raw tweet text itself. Let's see the number of impressions, and maybe let's see URL clicks as well. So now we're going to interface our near text semantic vector search component. So we do that by having the near text filter, and then we have this argument concepts in which we're going to pass in natural language processing. So jumping ahead a little bit in the talk, I'm also going to be looking at adding other Twitter users as well. So we're also going to add this where filter where we have path. All right, we'll pass on this for now, but anyway, so it might, let's see if this works. Okay, anyway, so we're seeing the return tweets of everyone I've added to the database, kind of jumping ahead a little bit, but we see how we get this idea of the top result doesn't exactly have the phrase natural language processing. Rather, it just has the idea of language models in it. So we see this retweet. Today we're releasing 3 new papers on large language models. This work offers a foundation for our future language research. So we can see who authored the tweet, because as we'll get into, and I know that I should have probably memorized the where filter a little more, but anyway, so this is the basic idea. You see how you can do a nearest neighbor text search into the database using the Weaviate console, and we'll get into further what this idea is about. So let's look at a particular example from my own tweets of the 5 nearest neighbors to Weaviate coding tutorial to further illustrate this idea of not having exact keyword matches, but really semantic matches with the whole content of the thing. So in this example, we have 4 Weaviate podcast episodes so far, and then this particular phrase, how to utilize the Weaviate database as a document store and haystack pipelines. This part of it is what maps it with Weaviate coding tutorial, I think. And I think it's an interesting thing just to visualize this idea of semantic search compared to just exact keyword matching. So you can also query data in Weaviate by using a Python interface for the near text search. We have a client query get, and then we have the near text concepts where we pass in the query, we execute the search, and then we index the return data object to access this in Python. So once we execute our search in Python, we can now easily do things like produce these matplotlib and seaborn plots, segmenting our data based on the impressions in the nearest neighbors to different phrases like Weaviate podcast or AI weekly update or Weaviate coding tutorial. So we see how we can easily kind of do this in Python to insert our query, whatever it is, natural language processing, computer vision, and then index the return data object on the impressions and then plot the impressions and see how it segments on these semantic categories rather than just symbolic values like what time the tweet was sent or whether it has a URL in it. So transitioning now into another project that I wanted to explore with this idea of Twitter and Weaviate is asking questions like, have I tweeted something like this before? Kind of like a pre-flight checklist before sending off a tweet. We might want to see if we've done a tweet that's been semantically similar and how well it's performed. So this is showing the idea of taking the same tweet, putting it into the search, and then seeing what's returned. But maybe more interestingly than just have I tweeted something like this before is to ask, have any of my friends or have any of some group, my company or people in a particular industry like machine learning or data science, have they been tweeting about this kind of idea recently? So to explore this question, I took the Twitter usernames of people who've been featured on the Weaviate podcast, and then I scraped their latest 100 tweets using the TweetPea API and uploaded it into Weaviate. And so that's why you saw the semantic search have everyone's tweets rather than just my own. So sorry to jump ahead a little bit with that, but so what you do is you use the TweetPea API, you get Twitter API keys, and then you just insert the username and grab the tweets and then add them into Weaviate. So another cool thing about Weaviate is you can have a flexible schema, like how the schema currently has the tweet text, the author, likes, but it also has impressions and say URL clicks. And this is data that I don't have for the Weaviate podcast guests, but I can still add their data into the schema, into the database by just the tweet author and the likes. So now that we have an understanding of what we're doing, let's have a look at the GraphQL demo to illustrate this idea. So again, we're looking at this idea of nearest neighbor search with different concepts. And the idea of this is we're trying to ask this question of, has anyone in my network been tweeting about this particular kind of concept lately? And we might also want to return things like likes to see how those tweets are performing and see if that particular topic seems to be successful. So let's take an example like generative art and say this idea of when you use neural networks to produce art, and let's see if anyone has been tweeting about this kind of idea. So we see that Han Zhao has been tweeting generative art, the exact keyword phrase match. We see the first three results all have this exact generative art phrase. This time we see AI generated artwork, so it's a little off from the exact match of generative art. We'd imagine this phrase has this vector space semantic distance to our query point of generative art. Bob Van Light tweeting generative models like Dolly for music. So to illustrate this idea where it doesn't need to be this exact match of the phrase, and then kind of this project where we can search through everyone's tweets to see if anyone is interested in this kind of topic. So now let's talk about if you're interested in playing with this yourself and you want to execute some Weaviate queries and do some semantic searches, let's look at the Wikipedia demo that is always hosted on the Weaviate console. So if you want to get this yourself before diving into it, you can scan this QR code to get the link, but also be linked in the GitHub repository that I'll show at the end of the video. But before getting into me doing the live demo, let's talk a little more about the graph-like data model of Weaviate, which is a really interesting detail that we haven't covered yet in the Twitter example. So in the Twitter example, our class was tweet, and we had properties like tweet text, impressions, URL clicks, and so on. But in the Wikipedia demo, we have two different classes, and they have named relations between them, as well as a recursive named relation back to itself. So we have articles in Wikipedia, like say the Miami Heat article that has a title, and then within the Miami Heat article, it has paragraphs. It has the actual content like that paragraph we saw earlier about the Miami Heat are an NBA basketball team, so on. And then we have the order, which is what order that paragraph appears in the article. So you have these named relations, has paragraphs, in article, links to articles, and this presents a pretty interesting interface to me for designing these data schemas and linking data between itself. So now let's look at the Wikipedia demo, which introduces a couple new concepts to Weaviate and also is something that is always available for people to explore. So the first thing that we're introducing is this cross-reference idea. So we're going to be linking our paragraph classes to our article classes. And again, we can see the schema of our data. We have the article, and then we have the title of the article, and then we have this named relation has paragraphs, which is the data type paragraph. And then we also have the other class, which are the paragraphs themselves. And then the other thing that we're adding to this is, in addition to semantic search, we can also add a question answering layer on top of the semantic search. So we return the paragraphs that are most similar to our query, and then we apply a question answering model that's been trained to classify an answer to a question in some context in order to produce answers to questions like, who was Stanley Kubrick? So to recap, Weaviate is a vector search database rather than, say, a library like Facebook's Face or Annoy from Spotify. And so what these vector search engines are doing is they have these approximate nearest neighbor algorithm structures that let you efficiently search for nearest neighbor vectors in absolutely massive collections of vectors. Imagine that we have millions or billions of tweets in our database and we want to find the most similar vector. We use algorithms like HNSW in order to speed this up. And what Weaviate is adding to this kind of approach is the full database support of create, read, update, delete, and having that kind of persistence layer, which is super important if you're dealing with massive amounts of data like this. And then Weaviate has this graph-like data model, which I think is really interesting. And to kind of come back to this tweet example, we could further expand our representations of tweets by doing this multimodal linking between text, image, data through this interface of the graph-like data model. So we have the tweet has an image, like how it has this cover image that's previewing the link. And say similarly, we want to have the tweet has article, and then we have another class article that contains the content of the article itself. So I hope this inspired your interest in Weaviate. If you want to get started with this, I highly recommend checking out the quick start guide from Weaviate. You can get started with running a demo data set, and it shouldn't be too long before you know how to add whatever data set you want into this kind of thing to enable these vector search functions. So to summarize, the fourth takeaway was about Weaviate for Twitter analytics, showing how we can segment the impressions of my tweets based on the contents of the tweets, like whether it's about Weaviate podcast, AI Weekly Update, and or it's about natural language processing, computer vision, and we can do this all with the vector search interface without needing to manually label our content to recover the semantic categories. And Weaviate is a vector search database that can be used to store and search through semantic embeddings of data. So that brings us to the fifth key takeaway, which are some research questions and discussion about this project and so on. So here are some of the most interesting research questions to me right now, and the first of which is this idea of, should I fine-tune or train my own embedding model? So earlier in the talk, I described this idea of sentence transformers trained on Wikipedia or save the data to vec model that can produce fairly good representations of all sorts of data with this zero-shot generalization idea. But it might be worth fine-tuning the models and looking deeper into that particular idea for very specific data domains. The next interesting thing are these ideas of large-scale vector search with approximate nearest neighbor algorithms, and understanding the behavior of these kinds of algorithms and understanding how vector search slows down once we have massive collections of vectors as well as very high dimensional vectors. I think this is another very interesting component of things like these vector search engine systems. The next question is about how vector search differs from classification or regression models and this general idea of retrieval augmented learning. And I'm sorry for taking a quick break. I see a message on the... Anyways, okay, so how does vector search differ from classification or regression models? So to come back into the Twitter example, we might want to have some model that predicts how many impressions a tweet is going to receive directly. So say this tweet receives 8,530 impressions, and we just have this kind of blind prediction. And say that's higher than our threshold, so we go, okay, great, I'm going to send this tweet. I'm happy with that number of impressions. Compared to the interpretability in a vector search where we have our tweet and then we can see which one of our tweets it's similar to, we can maybe also imagine this retrieval augmented prediction where it returns the nearest neighbors and then it uses that to make the prediction. It has this human-computer interaction where we can see the nearest neighbors that are impacting the prediction, and overall gives us more of an interface to be doing this predictive analytics with things that data scientists are usually interested in. So generally we ask these questions like, should I post this tweet? What might be a better time to post it? What would be a better phrasing of this tweet? And I think this vector search interface enables us a much more flexible way to answer questions like this. We might connect to our team, as shown in the podcast example, and say, has anyone on our team tweeted something like this? Who on our team would be best fit to tell the story? And then generally, as we look at companies and all these topics that we could be tweeting about, like these, different features of the software, different research areas, what topics should we be tweeting about? What is generally the performance of each of these kinds of tweets in, say, the market of social media attention? So to summarize, we're looking at questions like, how can we improve these systems with, say, fine-tuning embedding models, or looking at hybrid models that combine BM25 representations with these vector representations? How can we get better retrievals, and what looks promising? And I think this idea of retrieval augmented prediction generally looks like a very promising direction for the entire scope of machine learning and predictive analytics and data science. So to summarize, here are the key takeaways on this talk on vector search for data scientists. We looked at this idea of segmentation in data science, how we can take metrics like impressions and how we can segment it to get a better sense of it by using other attributes like what time it was posted, whether it has a URL link, and so on. The second key idea was to understand vector representations of data. How do we get vectors that represent our data? How do deep learning models, how are they trained to produce vectors, and what determines semantic similarity between vectors? The third key idea was to illustrate a few more examples of vector segmentation, looking at, say, separating houses or music and all kinds of things to just further expand on this idea of how we can segment analytics based on high dimensional semantics rather than just the Twitter example, and just kind of expanding the thinking of that. The fourth example in the Weaviate example, I hope you found that interesting as a way of looking at Twitter analytics, showing you roughly how to define a schema, how to upload data from something like Google Colab into the Weaviate cloud service, and how to do semantic nearest neighbor text queries using that GraphQL console or also the Python code. And then finally, we looked at some research questions and discussion around the project. And if you're interested in this, the slides from this presentation, a Google Colab notebook that shows you how to do this, and a recorded video presentation are all available on github.com/cshorten/vector search for data scientists, with the dash hyphen between each word in vector search for data scientists. So if you want to connect with us, please check out our Weaviate Slack channel. We're on YouTube at Weaviate Vector Search Engine. I'm the host of the Weaviate podcast, where we have all sorts of interesting discussions with people who work on research or are building particular things with Weaviate. And you can also connect with us on Twitter at Weaviate_IO. And finally, thank you so much for watching, and special thank you to Sebastian Widelek in advising and counseling the development of this presentation, and Svitlana Smolyanova for visual styling. I'm so grateful for the Semi Technologies team for their help in bringing this presentation together, and I really appreciate it. So again, thank you everyone so much for watching, and I'd be happy to answer any questions.
Thank you, Connor, for your session and for your time for delivering it. As of now, I don't see any question coming. Maybe someone's still typing in, so let's give it a minute on that. I will just quickly remind that the attendees will receive the short survey right after the session ends. Please take a moment of your time to fill it in. And in addition to that, all this Q&A channel will be around of the conference and even afterwards. So if you don't have any questions as of now, but you will watch on-demand video, for example, a day after the conference or tomorrow, and you will have any questions, feel free to reach out to Connor to the channels which he mentioned, or as well in this chat, you can always start the conversation with the network with the other attendees regarding that. So that's major it from my side. Connor, do you have anything else to add that you would like to point it out to?
Oh, no, just yeah, maybe if you're interested, the GitHub repository shown here has all this content available if you want to see things like the Google Colab notebook for exactly how to upload the data, or a recorded video presentation to go back through any particular thing in the presentation. And thanks again for listening.